The shortest version of the title for this video that I could come up with was making your games go faster on Threadripper. But not necessarily. Well, at least I want to explain it, because there's not necessarily a silver bullet solution, but if you understand what's happening under the hood, you can probably make some better choices about how to organize your system. And also, this is a really good video from a computer science standpoint about NUMA, non-uniform memory access, and the consequences of NUMA versus UMA. And we're going to use Threadripper processors as an example, but I've also got a nice dual Xeon system in front of me, or at least it was a nice system at some point in the distant past, about 10 years ago. This is Dell R710, it's a dual Xeon, you know, tons of memory slots. This is our model that we can use for learning. So I guess it's exciting, maybe, NUMA. I mean, if anybody's going to make non-uniform memory access exciting, I'm your guy. This is the quietest Threadripper system ever. This is a 1950X in here, and you know, I've got my lav mic on. We don't really do a lot of audio treatment because we don't know how. So it's pretty good. It's a pretty good, pretty quiet system, which is really super exciting. And this is our Dell R710, which really I'm just going to use for explaining stuff. It's really about CPU topology. So like, this is what, if you're not familiar with computer science or you haven't made it that far into your computer science classes, CPU topology. What is the topology of the CPU? And just like, you know, a topographic map where you've got mountains and rivers and valleys and all this kind of stuff, it's a map of sorts for how stuff's laid out in the system. So if we take a look here at our R710 system, we can see that we've got some expansion slots in the back here, and we've got two CPUs, that's what these are, and two banks of memory. And so if you look at the inside cover, it'll say, you know, these slots are associated with this CPU, and these slots are associated with that CPU. So like this CPU would handle this memory and this I/O, and this CPU would handle this memory and this I/O. But when you use a system like this, it doesn't actually show up as two different computers. Did Intel just glue two computers together? Well, kinda, yeah. I mean, there's an interconnect between these two CPUs called QuickPath, and it's an insanely fast interface for the, you know, CPUs of this time. In Threadripper, it's called Infinity Fabric, and instead of being two physical CPUs, it's actually all in one package. AMD has taken their Zen dies, like you would have in a 2700X, for example, and put two of them in the Threadripper 2950X, or four of them in the 2990, although it's probably a 2700 and not the X for the power considerations for the Threadripper. And then of course EPYC CPUs, which are AMD server grade CPUs, are the same deal, but those CPUs, you can actually run two of them in a system as well, and there's an interface that goes through the socket and all of that kind of stuff. So we've got two banks of memory, and each bank of memory is serviced by a CPU, but if CPU 1 needs something from CPU 2's memory, well, it can request it through QuickPath, and the other CPU will service the primary CPU's memory request for, you know, the memory, or I/O, or whatever. So then you might be asking, what is the topology of Threadripper? And that is a great question. Threadripper is the first CPU, to my knowledge, that has at least mainstream, that has a configurable CPU topology. You can use the Ryzen Master software to determine if the 1950 or the 2950 is a NUMA or UMA CPU, uniform memory access or non-uniform memory access. And the reason it lets you pick is because even though it's technically NUMA, there's so little penalty for the way that the CPU is put together that you can get away with running UMA, uniform memory access modes, for most operating systems, and that actually helps you instead of hurts you, except in some scenarios. And that's really what this video is about, so we're going to talk about that. But this also has implications for the recent Meltdown and Spectre vulnerabilities. So we're talking about, you know, speculative execution and what speculative execution means. And Intel is a little bit more affected by these issues than AMD, because AMD is a fundamentally new microarchitecture that was designed at a later point in time where some of these things were taken into account. So it's a different critter between Intel and AMD, but I'm getting a little ahead of myself talking about stuff, but it is really super, super exciting because of the consequences of new computer science and the security vulnerabilities and all the stuff, and but wait. What does this have to do with uniform memory access or non-uniform memory access? Let's take a look at some CPU topologies. Okay, let's take a look at the NUMA mode of our 1950X. This is a diagram that shows you the layout of the stuff in the system. It's pretty easy to understand. You can see that we've got our 8 cores, and we've got 2 CCX complexes. We've got our L3 and our L3. Those are our 2 4-core CCX complexes on the same piece of silicon. And then we can see that we've got another piece of silicon set up the same way. Over here on this side, we can see that we've got PCIe devices like 1002:67C4 and 1022:43B6, and then connected to that device is 8086:1533, 8086:24FD. These represent PCIe devices, and on Linux you can do LSPCI and see what your PCI Express devices are. It isn't really super important on Windows for you to know which PCI Express IDs go with where, but I can now tell you, I can give you sort of a preview of why GTA 5 is faster, and you can tell by looking at the picture. So if you were to run GTA 5, which doesn't really need more than like 4 cores, you can tell GTA 5, hey, don't ever run on anything other than core 4, 5, 6, or 7, which is really like 8, 9, 10, 11, 12, 13, 14, 15 because of SMT. So SMT's multi-threading, it's like AMD's version of Hyper-V. So you can see that we've got our 8 cores and 4 threads, and when we do that, if our graphics card happens to be connected over here, then all of the I/O that Grand Theft Auto needs to do in order to communicate with the memory and communicate with the graphics card and the CPUs that it's been assigned to, all happens here. If the CPU, happens to be, like if we tell it these CPUs, but the graphics card actually ends up being attached down here, then this NUMA node has to communicate with that NUMA node. And even though we don't have 2 sockets in our Threadripper system, Threadripper is basically multiple CPUs on one carrier, so there is a penalty or an overhead for communicating between those 2 pieces of silicon. There's basically 2 2700Xs in a 1950, so from one to communicate to the other, because one's doing the processing and the other one is handling the graphics card, that actually will hurt things in terms of low latency performance, which is where a lot of the time the really high frame rate benchmarks come in. And so that's why I sort of have been laughing at people that are wigging out over super high frame rate graphics, because it's really not about the system being slower in terms of computational horsepower. It's about the system being a little worse in terms of latency. But the reason it's worse is because the scheduler and the operating system don't take into account how things are organized the best way ever a lot of the time. And some operating systems do actually take into account how things are arranged, like depending on which program that you're running, which can actually hurt performance. So like, let's say that you're running 7-zip or something like that. Well, Windows doesn't handle that particularly well either, because it will say, oh, we're running these processes across NUMA nodes. That's not going to be really good performance. Let's not do that. And that's because it's optimized for a situation like this, where we're working with this server, and this server, there is much more of a penalty to go from one CPU on this server to another CPU in a different socket on this server because of the memory and all this other kind of stuff. The penalty with Threadripper is relatively low for those same kinds of operations. And if you've been paying attention, this system has 64 gigabytes of memory. 32 gigabytes is associated with this NUMA node, and 32 gigabytes is associated with that NUMA node. Now, with the 2950X and the 1950X, if you turn it on in UMA, it will lie to the system, lie to the operating system, and say, okay, everything is all connected to one place, all the buses connected together, and all of a sudden the scheduler can't really take advantage of the true topology of Threadripper. And so if you are in that situation, that's why they have like the game mode thing. And most of the time, if you just take a little bit of care, you can run a PowerShell command or other configuration option and actually say, hey, for this game, I want to run on this number of cores, and you run it on the cores that you know are associated with your PCI Express device. And even if you don't know that, even if you don't want to use Linux and run ls topo to see what your topography is, there are tools for Linux that will let you do that, or there are tools for Windows that will let you do that. There's tools for most operating systems that will let you do that. And by doing that, you minimize how much travel over the rest of the system, that information does. Now, if you're running GTA 5 at like 4K, because you need a lot more computational horsepower and because the graphics card has trouble keeping up so the frame rates are not as high, these kinds of issues matter much less. And the reason for that is, again, not bandwidth, but really latency, because the graphics card needs more time to process a 4K frame, which means that it is more tolerant of more blips of latency in between the data being taken from memory, delivered through the system bus and to the graphics card. When you're talking about 150 or 160 frames per second, that little tiny extra hop on the Threadripper CPU to go from one die to the other die could cost you 5 or 10 frames per second at 160 frames per second. But at 4K, it's going to make a difference of like 1 or 2 frames, because the latency, the bottleneck is not the Infinity fabric. The bottleneck is not the 2 CPU dies on one piece of hardware talking to each other anymore. It's in the graphics card or the system bus or somewhere else. So then you might be thinking, what about the 2990 WX? What kind of monster is that? Well, that's basically a server part for the desktop. Now, the 2990, unlike the 2950 and the 1950, AMD does not give you the choice of running in UMA mode or Uniform Memory Access mode. And the reason for that should be apparent from looking at the topography. So if we look at the topography, we can see that we have 4 NUMA nodes. 2 of the NUMA nodes have all of the memory and all of the peripherals connected to them. The other 2 NUMA nodes don't have any memory or peripherals. That means to load information into those processors to be able to be processed, it's going to rely on the other nodes in order to be able to do that. So that's one of the reasons why the performance can regress. Like if you look at the benchmarks from AnandTech or the Phoronix benchmarks, the Phoronix Windows versus Linux benchmarks, the performance can regress when you're running certain workloads on a 2990 versus a 2950. You would think that a 2990 is always going to perform very close to a 2950, because worst case scenario, you just don't use the cores that are on these hidden NUMA nodes. This is what that term means, that the node is hidden, meaning that it doesn't really have direct access to the system. And Intel was actually the first company to do that. Some of the high core count Xeons are basically hidden from the system. They might have direct memory access, but they don't have direct access to the bus. And that was also a source of bottlenecks in certain workloads on the Intel side of things. But if your workload is such that you aren't bottlenecking memory, or you're not bottlenecking your bus, then you could keep those extra CPU cores fed. And so that's why certain types of tasks, like rendering tasks or Linus Torvalds with compiling the Linux kernel and all sorts of stuff like that, can really, still help in that situation, even though these CPUs don't really have direct access to the rest of the system. I mean, they still have 16 megs of cache each. They still have 8 cores each. So it really does add a lot to the system to have those, just not as much as it would as if it were the server counterparts. And this is also sort of the difference between this Threadripper part and the EPYC part, because the EPYC part, which is AMD's server CPU, it does have the extra memory and I/O connections for those CPUs. So your peripherals and your memory can be split among the dies. And so just like this system has several different CPUs and the peripherals are routed through it a different way, you could do the same thing in the server version of the CPU. So it's really sort of exciting. Now, I mentioned about mitigations and things like Spectre and Meltdown. One of the vulnerabilities on the Intel side is when you switch from a system process to a user process, the level 1 cache memory, level 1, get it, is not flushed properly. And so if you look at this, we can see on our diagram that maybe I'll be running a program and we've got instruction and data cache, instruction and data caches at the level 1. And if I run a program and it loads a program and it's executing, and then that's a system program, and then I switch to a user program, the user program would be able to read, at least on Intel CPUs, the contents of the cache memory, which may contain passwords or encryption keys or other sensitive data. So the fix for that has been to just flush the level 1 cache when you switch contexts or switch processes. If you use Windows really seems to prefer core 0 on your CPU. So if you've got a 6 or 8 or a 16 core, whether you've got a 2700X or a 2600 or the 6 core Coffee Lake or whatever CPU that you have, if you can tell your games and other stuff to not use core 0, you will generally have a little bit better performance. Not always, that's not true of every game, but there are definitely reports on the internet of people going into Task Manager and changing the CPU affinity. That's what that's called. So when you run a process and it's like, this process should only use this CPU core and this CPU core and that CPU core, that's the CPU affinity. And so when you configure your process to only use specific CPUs, those types of penalties from switching from a system process to a user process basically go away. There are always some penalties with switching process contexts like that. It's just that the recent fixes on the Intel side of things to just flush the level 1 cache, that's really bad. You should never flush anything level 1. That's just, you shouldn't do that. They're gonna have to fix it in hardware. But I think with the high core count CPUs, I think that we're going to see a lot of innovation in the scheduler. Microsoft and the Linux people and really everybody that's working on these mitigations, you can probably run the system processes on one group of cores and user processes on another group of cores, and then only when the system really gets overloaded do you start sharing user and system processes between cores. Because hey, with the 2990, got 32 cores to work with. And really, I want to have all my user processes running on the 16 that are directly connected to something. And I would want my background processes to run on the cores that don't really have direct access to anything. The scheduler knows best. The scheduler is the thing that can see where everything is, and you as a user generally should not second guess that. But because this is new hardware, it's probably going to take a year or two before everything really catches up and everything is running as optimally as possible. So using the info from Linux, or ls topo command, we're able to associate Grand Theft Auto to only run on the 4 cores, 8 threads that are on the other side of the CCX from the system one, but that is also physically connected to the graphics card. So at least running the benchmark at 1080p makes about a 7-8% difference in the maximum frame rates, which is pretty encouraging. Now you don't have to use process lasso. You can totally use the PowerShell commands and set the processor affinity that way. With PowerShell, just get process name and set the parameter that way. That's totally fine. You don't have to use process lasso. But it's surprising that that makes as much of a difference as it does. Now the really interesting thing is that even when the processor is in UMA mode, it makes a little bit of a difference, although not as much. And I think the reason for that is probably because Windows doesn't know where to allocate the memory. It's possible that we're still getting some of the GTA 5 memory allocation that is actually on the opposite side of the chip. It's the opposite memory controller, and maybe that's why the slowdown. But we at least know the I/O because it's pinned to the same cores, and that's true whether or not you've got NUMA or UMA installed. And we know that those cores are associated with the graphics card, so that's why our GTA performance is still improved a little bit, even in UMA mode, just running this test. It's pretty interesting, I think, and something that maybe deserves even a little bit more experimentation. But GTA 5 is an old game, but I understand the engine and how it works and how the engine breaks, so it's sort of useful to test, I think. I bet you never thought there was a relationship between security mitigations, level 1 cache flushing and cache affinity and processor affinity, GTA 5 and getting GTA 5 to run faster, and the topology of your system, which PCI Express peripheral is connected to which group of CPUs and which memory. Oh, and by the way, in case you're wondering, I didn't tell you how to, make sure that your process is running with memory local to the CPU that it's executing on. Don't worry, everything automatically takes care of that. Windows doesn't in UMA mode, but in NUMA mode and Linux and all this other stuff, it definitely does completely take care of it. And in case you're wondering about numbers, the latencies that we're talking about, so the memory latency going from a local Zen core to DDR4 is about 60 to 70 nanoseconds. And the latency from going from a far CPU core to memory that's through another node. So like if I wanted to get from one of these cores down here to NUMA node P2's 16 gigabytes of memory, that's gonna be more like 135 nanoseconds instead of 70. So we're still on the scale of nanoseconds, but there's a big difference between 70 and 160 nanoseconds. But at the same time, the bandwidth is really high, so I can get 32 or 64 megs of data into that core really quickly, and then the core can process it. And as long as that core is not processing stuff faster than I can get stuff in and out of it, I'll benefit from the CPU performance. If the CPU is processing stuff more quickly than I can get stuff in and out of it, it'll bottleneck and we'll see those performance regressions. So maybe with this information, maybe with this knowledge, those benchmarks that you see around the internet will make more sense. And if you've got a system like this, you should experiment with telling your games not to run on Core 0, just to see what happens. Maybe it'll help. Maybe not, I'm not really sure. There's also a program for Windows called Process Lasso. I've been talking to the Process Lasso guys, and they're gonna add support for making Process Lasso more NUMA aware. But Process Lasso automates a lot of stuff that you can otherwise do at the command line. I mean, with the PowerShell commands, which if you go to the Level 1 forums, there are some example PowerShell commands that go with this video that you can use for setting your process, so you don't have to buy Process Lasso. But Process Lasso makes it a little easier to save and restore profiles, and it also prevents Windows from doing some obvious dumb stuff. So it's a pretty useful program. You can check it out. There's a trial for it. This is not, sponsored or endorsed or anything by Process Lasso. I just thought the Process Lasso on Windows, especially if you're working with the 2990, could be useful. And maybe AMD could build some of those features into the next version of Ryzen Master. Fortunately, I don't think we're going to see a UMA mode for 2990s, but for the 2950s in UMA mode, for certain processes that are known to not perform as well in UMA mode versus NUMA mode, maybe that would be useful. I don't know. If this is still clear as mud, come to the forum, because I got to learn to make better videos. I'm Wendell, I'm signing out, and I'll see you in the Level 1 forums.